Hi, we're Team 23. Our project is about non-parametric modeling of microbial growth. So what is a non-parametric model? Basically, the predictor does not take a predetermined form. The model is constructed based on information derived from data. This is critical for our project because for data that we are working with, there are two key challenges. First, when microbes are grown under stress conditions, they follow a non-sigmoidal shape that differs from traditional sigmoidal curves, just as how the green fitted line deviates from other curves in Figure 8. Parametric models like Logistic and Gompers fail to most accurately capture non-sigmoidal growth as shown in the residual plots in Figure B. However, non-parametric Gaussian process model solves this issue by incorporating prior knowledge and providing uncertainty measures over predictions in the shaded credible intervals. Second, we want a model that can deal with batch effects. Sometimes the same experimental design ran in different machines can provide very different growth curves. GP model is able to account for this by using GP priors or kernel functions with kernel hyperparameters. GP model is thus more effective in predicting growth under stress conditions compared to other parametric models, indicated by a better shaped alignment of the regression curve with data points, as well as lower MSE value.
So next, let's talk about the phenom model itself. So the phenom model is a hierarchical non-parametric microbial phenotype model that uses Gaussian processes. In its current rendition, it allows scientists to input a data file and a meta file and it outputs all the points predicted by the model. However, from troubleshooting, we found two main issues with phenom: the runtime and statistical errors. The runtime of phenom varied heavily with both the number of time points and batch effects, as you can see in the graphs. However, it seems like the batch effects had a much more significant effect on the runtime. This could be because of how phenom was designed to make the GP models for not only the batch effects, but also the relationship of batch effect and fixed effects. Thus, more batch effects leads to exponentially more models formed. Another issue we found with phenom were the myriad of statistical errors that plagued the sampling. The biggest of these errors were the divergent transitions. Essentially, this error shows that parameter estimates are biased. The other errors include the high R-hat values and the low effective sample size, which all indicates issues with the sample. To find solutions to these errors, we graphed some of the major parameters, from which we found a relatively even distribution of these errors. This pushes us to believe that it could be more of a sampling issue rather than phenom's model having an issue itself. We then proceeded to adjust the sampling parameters for a slower sampling process that would be less prone to errors.
The output matrix from the phenom model is very dense and hard to extract biological meanings. So we created a pipeline that put the output expected means and SD values and the input values into one graph. Scientists can better observe how well the curve and credible intervals fit their data points for every combination of experimental conditions under the same scale, allowing comparison of phenotypic differences across multiple control variables. Our pipeline also generated two auxiliary graphs for data analysis. First, the optical density functional difference graph comparing the mutant and parent strain over time, and second, the heat map, which examines the relationship between growth trajectories by clustering phenotypes based on change in optical density that can be later studied in gene regulatory network topology. These graphs proved to be significant for biologists because they provide more information than just a binary is growth different.
This is how the workflow looks like for biologists. Thank you.